So let's talk about, if it's okay, let's kind of segue into what we did in 2013 and kind of catch you guys up on more field data for Allison. In 2013, we were really all about collecting some hydrologic data up in that area that I called the centroid. So we took advantage of existing monitoring wells, actually. So these are wells that really aren't designed for the kind of studies we did, but we certainly took advantage of it and viewed it as an opportunistic situation to come in and do some work at R42 and R28. Again, those are the wells that kind of define the centroid of the plume. And one of the key objectives was to figure out that if the time comes to go in and sort of pump out chromium mass out of that centroid, how do we do that most efficiently? So the kind of data that comes out of the studies like we did in 2013 really helps with that. We also want to evaluate whether or not some chromium in hexavalent form that sits in that perched intermediate horizon that happens to be monitored by a well called SCI2, whether or not we might actually be able to efficiently get that mass out of the aquifer as well. It's probably worth noting that the concentrations in SCI2 are around 500 parts per billion compared to the kind of the centroid of the plume where concentrations are closer to about 800 or 900 at their maximum. And so we did these studies at these wells, and I'm going to kind of work my way through a few slides here that kind of describe a little bit about the kind of data that we actually learned from that. This stuff's pretty hot off the press. We do have a report that's going to the New Mexico Environment Department. Actually, I signed it out this morning, so it should be coming to the Environment Department within a couple of days. That really kind of pulls together a lot of this information, so certainly you guys might be interested in looking at a much more in-depth review of those data than you'll see here today. But we were interested in this concept of kind of capture zone. So if we were going to go in and try to pull a bunch of mass out of that centroid, you got to be pretty smart about how you go about doing that kind of thing. It's really important, and I'll get into this a little bit today, but it's really important to understand the contaminant behavior during pumping. And what I mean by that is when you go in and you think you can put a big horsepower pump in there and start sucking a bunch of contaminant out of the groundwater, how's that contaminant really going to behave? Is it going to stay at the same concentration that you started at? Is it going to increase? Is it going to decrease? Because you don't want to go in and build something and think you're going to get a bunch of mass out and find that after pumping for 2 weeks, your concentrations have dropped by 2/3 or something like that because your efficiency really goes down. So it really helps you understand how to do this work. This project last year involved needing to manage a lot of water. So we were one of the key issues for us in a project like this, because right now we don't have a sort of a dedicated long-term water disposition component to this project yet. So part of, besides all the environmental studies that we're doing, is really understanding how we're going to disposition the water. For the studies in 2013, the scale of the work was essentially relatively small enough that we were able to land apply the water. So we were pumping water, and I'll get into that in just a moment, on a daily basis, 24/7 for about, what was it, 5 months, all said and done in Morton-Dade Canyon, and we needed to disposition that water. The permits that we worked out with the Environment Department allowed us to essentially run kind of a treatment train like the one described here, and I'm going to walk you through all the components. This is just a little air photo, kind of actually standing up on the cliff, looking down at one of the site operations areas. This is a conceptualization of the well. We would pump the water from the well, and each one of these little bow tie looking shapes are places that we would collect samples for various purposes. This is the port that we kind of called our science samples. This is where we were understanding how things were changing downhole as we pumped. That water was pumped into above ground holding tanks. It was run through a treatment system that involved ion exchange as the method for essentially stripping out the chromium from the water. So it basically just takes almost 100% of the chromium out of the water as you run it through these resin chambers. Then we would run that treated water into these holding basins like this, and then about every 2 or 3 days a series of trucks would come through and quite literally pump out water after we had determined that it met all the land application criteria, which are very low limits set for us by the Environment Department. And then we sort of had a loop track down in the canyon floor. We would drive around that loop and spray the water, the treated water, onto the ground. It was the cleanest site on the Pajarito, or the greenest site, I should say, on the Pajarito Plateau last year. And really, besides the fact that it helped us disposition all this water, it was actually an excellent pilot for us on how we can manage potentially much larger volumes of water that we may generate in the future as this project evolves.
Danny.
So this is just a photograph, real quick. Did I hear?
Danny,
Carlos.
so I understand that we were pumping and treating 24/7 for 5 months, but I guess for over the winter months, we stopped?
We did.
And-
And actually,
Okay.
I'm sorry, I cut you off.
And when are we going to start again, and are we going to go back to that same schedule?
Yeah, so the reason we stopped was because these particular permits for land application, one of the conditions of the permit is that you don't generate surface runoff. So you've got to make sure it's always soaking in gently into the ground. And so nominally around Thanksgiving of every year, these canyons, the soils freeze. And so water that you would land apply actually can start running off instead of soaking in. And so we shut down operations at the end of November, really under permit terms. But our experiments were accomplished by that time as well. So it was not a problem, and we had actually scheduled around that. We do have some additional tests, to answer your question, this year. And I'll get into all those here in just a moment, if you don't mind.
Thanks, Chairman.
Okay.
Danny, real quick question. How much water are you guys pulling out a day, week, a month?
In these studies, so the two wells, R28 and R42, R28 pumped at nominally around 29 gallons per minute, 24/7 for the 2 or so months that it operated. R42 was pumping at about 8 gallons per minute. And those numbers were really just numbers driven by what those wells can produce. They're monitoring wells. They weren't really designed for large-scale hauling of water out of the ground. So we went in there and looked at the data from aquifer tests and tried to maximize the pumping rate, because that you want to push the aquifer as hard as you can with these kinds of tests. And what we figured out was that we could do R42 at about 8 GPM and R28 at about 29 GPM.
So just, I guess it's a related question, three-part. So where is this water going when you pull it out? Do you need any permits from the OSC?
We do not need OSC permits for this because this is all considered testing, essentially. Our permit requirements were through the Groundwater Bureau at the Environment Department.
And what impact is it having on the rest of the aquifer? That's
None
not
whatsoever, and
contaminated?
I'll show you a little bit about that as well.
Thank you.
Yeah. So this is just one of the well housings. And thanks for the questions, by the way. These are great. This is just the well housing, electrical system, and some of the infrastructure in the background here, just to kind of give you a sense of what this really looks like. These wells are, at least in this state of condition, are pretty unimpressive, I guess, if you will. All the real action's about 1,000 feet below ground. These are what the treatment vessels look like. So when you hear people talking about ion exchange treatment vessels, these columns here, these chambers, I don't know, what are they, maybe about this big around, something like that. They're filled with a resin that basically just grabs all the chromium. And there's nitrate in this groundwater as well, below standards. But these resins were optimized for stripping out all the nitrate and all the chromium very, very effectively. And we run these things in series. And I don't know if you remember in that conceptual diagram, but it showed sample points of water going in between chambers, on the outside of chambers. So we're sampling this all along the treatment train to evaluate, essentially real time, the effectiveness of these things, and also making sure that water that might exceed any kind of land application criteria doesn't get by us without us knowing it. But we also learned a whole lot from this study about how long we can expect one of these ion exchange chambers to last. You know, how much capacity, how much rate of throughput can we put into these things, and it's really going to help us optimize our treatment systems in the future. These are the holding tanks. These are 20,000 gallons apiece, and basically they're just a reservoir to basically hold water kind of in that treatment train process. This just shows you that neither rain or sleet nor snow or wind stops our actually, we photoshopped this snow into this slide just to remind people that once upon a time. Now, this was actually that snowstorm that we had in November. I thought that was worth showing just to, it can snow here, believe it or not. So here's the kind of data that we collected. And I'm not necessarily going to go into all the detail on these plots. Obviously, they're very busy. And if you're interested, you can certainly see more about them in our report.
Excuse me, Danny.
Okay.
We can go back. How do you clean those tanks?
We actually send them, so Siemens, I don't know if you noticed on the,
Right.
Siemens is the supplier for this, and they regenerate. We don't do it on site. We ship the containers back to Siemens, and they regenerate them and send us back fresh chambers ready to use.
And how often do you do that?
We actually never had to do it last year with all of this work. Yep, we never hit saturation on any of the
What's
the
our
chambers.
capacity then? Ish.
You finally hit me with a question. I don't know the number. Maybe if Dave remembers, or Jeff if you do, but I don't remember what total capacity is. But let me put it this way. We think we pulled out about 13 or 14 total pounds of chromium last year with these two studies. Not huge amounts, but these things didn't come close to saturation with that. So that's some context, but not surprising that they didn't saturate with only 13 or 14 pounds.
If you were to need to replace, how would it be transported?
You know, I'm not a transportation expert on this, but one of the things we did learn was that they would not be classified as hazardous waste, and so that they could go manifested as non-hazardous waste. And I think the regeneration site is in Minnesota.
Okay, thank you.
Danny,
Carlos.
so if we know how big the plume is, more or less, and we know how fast we can pump and treat, what is your best educated guess as to how long it would take to clean that plume?
My education doesn't go there, Carlos. Yeah, but yeah, exactly. So again, you guys have read ahead, and that's really not fair, but it's making you look good. If you can hold the thought,
Okay.
and let's see if we get close to answering your question towards the end. Man, yeah.
Well, you know if it's coming from the perch aquifer or it's coming from the groundwater?
We are 100% sure it's coming from the regional aquifer. There's no connection when you pump in the region. These wells are only screened within the regional aquifer. There's no hydrologic no direct hydrologic connection. This is a very complex slide, and I'm not really going to go through it, but it's really just to kind of show you one of the ways that we analyze these data. One of the things we showed here is there's a bar that shows that PM4, which is one of the LA County's water supply wells, was pumping during this whole period. So obviously it's summertime, people are using water in the town site, and it does generally create a drawdown all across the plateau, not just in the area of the Chromium Plume, but all across the plateau. There's a bit of a drawdown that occurs every summer during sort of the peak pumping for gardens and lawns and stuff like that that occurs in any municipality. And that's what's representing this kind of overall decrease. You should note the scale on this thing. This is 5,835.6, 0.4, 0.2. So we're not talking major drawdowns. This is all on the order of a half to maybe 2/3 of a foot total drawdown from pumping in this area. But if you analyze these data real carefully, and you can do it with your eyeball, and we've done it with our eyeballs, plus with computer models, you can see slight inflections that occur where things kind of turn a little. There's little bumps here and there. And we've analyzed all these data to basically come away with an understanding of basically how pumping at those rates we talked about, just 29 GPM and at 8 GPM, not big whopping pumping rates, how they're affecting the regional aquifer. So when we were pumping at those two wells, we had about 10 or 12 wells in the area surrounding it set up with automated monitoring instruments that were making a recording about every 5 minutes of how the pressure, not necessarily the water level, but how the pressure at those locations was responding to these wells. And that just gives us a sense of the hydrologic complexity in the area. It helps us really understand the aquifer in a way that when I'm trying to tackle Carlos's hauling mass out of the ground, I understand what I need to do to be good at it and how many wells it might take to have overlapping zones and things like that. So that's what we mean when we say capture zone analysis. And these kind of data really helped us learn a lot about the aquifer in that location. This is just a conceptualization of sort of the field affected by the pumping. So coming back to those two wells, there's R42 right here. It's the one that pumped at 8 GPM. Here's R28 right here. It's the one that pumped at about 29 GPM. And this sort of ellipsoid right in here is the one related to R42, and it shows that it really didn't have a very large zone of influence. So this line generally approximates everywhere where we could measure about a centimeter of pressure response. So we're talking this. I mean, we're down in there with our magnifying glasses looking at these data, trying to see if there's any evidence of a response. But it's just a conceptualization that, you know, and the shape is somewhat controlled, obviously, by where we have data. And so everywhere where we had a well that we could actually measure response, and when you see two values like this, that's that top screen near 25 feet below the water table, and then the deep screen, maybe 100 feet below the water table. It shows the difference in magnitude. So that's 2 centimeters, that's 6 centimeters, there's 11 centimeters. This one actually responded similarly at both. There's one that was 11 centimeters and 0.14, higher in the deep zone. Very interesting piece of information. So we kind of pulled all this together to kind of generally conceptualize that range of influence. Whoops.
Question?
Yeah.
Is the influence proportional, R28 pumping 3.5 times more?
It's no doubt related to the pumping rate.
Is it proportional, though? The effect?
I don't know. I wouldn't say necessarily, because another major factor is the permeability and the hydraulic conductivity around that well.
Okay.
So one of the things that really told us, and I'm going to get into that in just a moment, is that R28, and we've all known this already from other aquifer data, that R28 is probably the most permeable zone that we see anywhere on the plateau. R11 is a little bit similar, but these two wells right here are really in a very unique setting where things seem extremely permeable right there. Okay? So this is not a speeding bullet. This is actually a conceptualization of how you affect the flow field around a well when you pump it. So there's the well, and let's picture that's well R28. And when you pump, the groundwater flow is following these blue arrows, left to right in the field here. What you actually do is you affect a fairly small area right around the well in the down gradient direction. And you tend to stress the aquifer in an up gradient direction shaped somewhat like this right here. And there's some simple hydrologic equations that help you calculate, based on pressure responses, what this length will be of where you start kind of grabbing water and pulling it in towards that well. It doesn't necessarily change the flow velocities in these areas. It just says that flow within this kind of capture zone, if you will ultimately make it into this well. Really important to point out, it does not change velocities. And this width is probably the most important aspect of this, because all this water is going to go towards there eventually. But understanding this width is really important for figuring out, if you ever want to kind of capture something in the regional aquifer, how many of these types of pumping wells you might need so that you have overlapping capture widths so that nothing gets through. We've estimated just from this study that width right there might be as much as 400 meters if you could sustain pumping. It takes a while to develop this to its fullest, maybe up to 6 months of pumping, but we could potentially get a 400 meter wide capture width in the vicinity of R28 with sustained pumping. So one thing that was really, really important for us to understand, I talked about the contaminant behavior during pumping, and this is what we call a time series, and I'm going to show you R42 first, and then I'm going to show you R28. But this is what the chromium concentrations did over time during pumping. And this was particularly interesting information for us. So the initial concentration at R42 when we started pumping was around, nominally around 900 parts per billion when we first started pumping that well. And this is the well that's pumping at 8 gallons per minute. And you remember, we're sampling quite literally every day coming out of this well. And so you see a lot of data plotted on here. But what's interesting about this is that the chromium concentrations decreased over a period from initiation of pumping on the 19th of June to when we turned the pump off on the 22nd of August. The concentrations decreased down to around in the high 600s, about 27% decline pretty quickly. It looks to us like they probably never did really ultimately stabilize. They might have. We're not sure if they would have continued to decline or if they were starting to plateau, but this was kind of within the constraints of our study design for this year. And then we turned the pump off, and it's important to kind of watch whether or not the contaminant rebounds. And in fact, we did see the concentrations rebound. This is just the water level in that well, showing the pumping period, and then you see the quick rebound when you turn off the pump, and stable water levels after that. But this curve is really important to us, and we haven't really fully digested why the concentrations decreased. You could think simply, well, you were pulling clean water from somewhere up gradient. That's one possibility, certainly. You could be pulling clean water from below you into the pump when you're doing that. Certainly a possibility. There's another possibility that we're particularly interested in, and when you think about these aquifer sediments, think of them as kind of bimodal. There's kind of two components. There's the coarse sands and gravels where most of the flow occurs, and then there's fine-grained silts and clays where water moves a lot slower and can kind of sit there sometimes for a long time. You might have a different chromium story in those fine-grained particles. Maybe we've had more reduction in those fine-grained layers, and the chromium concentrations in those areas are lower, and we were starting to finally pull from some of those fine-grained layers during pumping. And then when you rebound, you begin to dominate again by the coarse-grained layers. That kind of thing is really important to know, because if you're going to go in, and this touches on your question, Carlos, if you're going to go in and you're going to do pumping, and you're going to ask me how long do I need to pump, I need to understand why things rebound, why things decline when I pump, and why things rebound when I stop pumping, to be able to really get at that question. Because that's that thing, is like, I could go in and say I can evacuate all these coarse portions of the aquifer over 5 years or something like that, but I need to understand what happens when I stop pumping to know whether or not I'm really done. And you don't want to go into a project like this sort of blind, thinking that, well, it's 5 years of pumping to get 1,100 kilograms out, turn around and a year later the whole plume is rebounded on you. So we're still trying to understand that. Here's the same basic story for R28. In this case, we saw about 20% decline and then rebound. But what was very interesting about this is that, and what kind of really suggests that idea that we were pulling clean material in, clean water, during pumping to cause the declines, is that here's chromium, again at R42 in this case. But here's some of the other co-contaminants that are located in this area, sulfate and nitrate in this case. And notice they didn't follow the same kind of pattern. This really seems to suggest that we were not probably pulling in non-contaminated water causing those declines. It is probably some more complex phenomenon at play. And in fact, in some cases, it looks almost like some of the constituents are following an almost opposite pattern to what chromium is doing in there. We have not fully chewed on these data yet. So when it comes to mass removal, there's two ways of looking at it. These two plots are just slightly different perspectives on it. Notice that this one's just plotted as number of days and chromium removed, cumulative chromium removed over days for a variety of wells. And this comes back, I think, Allison, to what you were pointing out. R28 took out more chromium than R42 did. It's pumping at a lot greater rate, lower concentrations, maybe around 300, but 4 times higher pumping rate than R28. So not surprisingly, it hauls more chromium out of the ground on a per day basis. Another way of looking at that same thing is to kind of view it as a mass removal efficiency. So what's the most efficient way to get chromium out of the ground? If you're going to embark on a big remediation project, not just in New Mexico where water is particularly precious, but anywhere, you really want to try to get just at chromium and not pull any more water out than you might need in the process of getting chromium out. So this part of the study really told us a lot, that at R42, even though it was only pumping at 7 or 8 GPM, we actually, on a per gallon basis, got out much more chromium than what we did at R28. So simple analysis, but really profound in terms of how you might strategize a chromium removal effort in the regional aquifer. Yeah, Carlos?
Are you finding anything else besides chromium?
Yeah, we pull out, so we have sulfate at low concentrations, we have nitrate. No other constituent is present in this area above standards, but there are other co-contaminants that are part of that, going back to that sort of mixed pathway description I gave you earlier. There are other co-contaminants that were either co-released with chromium or have mingled into the area from adjacent areas. But they're really mostly at extremely low concentrations. The only one that even approaches standards within the chrome plume itself is nitrate, and it's about half standard.
Danny, are there any other areas in the country that are doing this type of mitigation? And if so, are you able to compare? And I know our our geology is a lot different than anywhere else.
Sure. Geology is different, but there are common principles, for sure, on how you attack a problem like this. And I would actually say we're quite heavily engaged in trying to learn lessons from around not only the DOE complex, but from industry as well. We're really trying to make sure that we don't do anything that's already been tested and tried in places, and we're leaning heavily on successes in other places and learning how to avoid other approaches from lessons learned in other places as well.
Are you, and I know this is all fairly new, have you been able to analyze anything from anywhere else, any other data that kind of shows the same reaction to other constituents?
We will be doing that and haven't had a chance yet.
Okay, thank you.
You're welcome.
So Danny, where do you think the nitrate is coming from? Is it possible it's coming from the rad liquid waste plant?
So there's actually
Former district?
possibly 3 sources of nitrate in here. We think the dominant one, the one that's co-located with the chromium plume, is nitrate from sanitary effluent that came through that same outfall. So I don't know if you're familiar with the sanitary, people call it SWISH, the sanitary wastewater system at the laboratory. So it actually routes treated effluent up to the head of Sandia Canyon and releases it. So we think the dominant portion of it is sewage nitrate, but we are able to actually fingerprint nitrate by looking at some of the isotopes, and we also see some nitrate in the area that appears to have come from nitric acid. So more from sort of rad operations and probably from rad liquid waste is the dominant one.
When you talk about chromium removed, are you talking about total chromium? Or just
Well, it's hexavalent chromium because no trivalent chromium. So in the groundwater, no trivalent chromium exists in a filtered or in anything that you're going to pump out of the ground. We've looked and we've done comparisons, and when we sample a groundwater sample and we report a number like 800 parts per billion or whatever, it's 100% hexavalent chromium.
Is this plume changing its shape at all?
Like I showed in that one slide, there's some evidence that 3 of the wells along the periphery might be increasing in concentration. I would love to imagine a situation of fast forwarding 10 years and seeing what the plume would look like. There's a chance that it's growing a little bit. There's a chance that it's just wobbling in place. We're not going to wait around 10 years to figure out which one of those scenarios is true. We're going to go get at this problem.
Thank you.
Okay, the hook just came out, so I'm going to kind of kick things up here a little bit. Perfect timing anyway. What are we doing now in 14? So 14 is going to be an extremely aggressive year for us. We've got a lot of work going on. Here again is sort of the conceptualization of the plume, and I've just kind of shown our activities here to kind of show you kind of what part of the situation we're tackling with each one of these situations. We are going to come back to SCI2, that perched intermediate well that I said we tried to evaluate whether we could pull some source out of that. We're actually going to turn that well on here probably within about the next 3 weeks or so and try to run it continuously until the ground freezes. We're not sure that there's that much perched water even in that zone, but we're going to find out. We're going to see what we can do to haul that area out of there. And then it'll be very interesting if we do deplete it to watch whether or not it rebounds, whether it recharges, and if so, does it recharge with chromium or not, or is it going to be clean water? So we'll learn a lot about that.
Will the rate be on that well?
What's that?
Gallons per minute for
Oh,
SC?
tiny, less than, it's a little bitty
teeny
2-inch
bit.
well, so we're going to be pumping at about a gallon a minute. Someone asked about whether we're going to be doing similar studies. We are. We're calling them aquifer tests. They're nominally about 45 to 60 days long. They're not at the same 2 wells that we did last time. We know what we need to know out of those wells right now, but there's some of the wells along the periphery. A well called R62, which sits right here. We're going to be working at R43. We're going to learn a lot about what's going on in those wells, and that's really going to help us understand a lot more about why this kind of back edge of the plume really even exists like it does. Coming back to a lot of the good discussion in that bubble chart about what creates attenuation. So when we saw those hexavalent bubbles move from the left side to the right side and become trivalent chromium, that's the term commonly used for that is natural attenuation. And so we're going to actually go in and collect some data, this time out of the regional aquifer, to find out whether or not those iron-bearing minerals are present in the regional aquifer to do some work for us as well. Because if we're going to go in and do a cleanup in here, the first thing you want to know is how much work is the environment going to do for you already, and what do you need to do on top of that to kind of take care of the problem. But you really want to make sure you understand whether or not the environment's going to do anything for you. So that's what kind of a category of natural attenuation studies. That's going to involve coring into the regional aquifer. We've got to start figuring out a variety of options on how we might disposition water if we ever get into a very large pumping program. And so we're going to be doing some mostly bench scale studies at this point, but we're also looking at some more creative ways to disposition large amounts of water as well, and that's going to be a big part of this year. And then probably our most important and biggest project this summer is a well that's going to sit right in here, and it's going to actually be designed as an extraction well. So we talked about the pumping last year for monitoring wells. This well is going to actually be designed like a water supply well would be designed. It's going to have a screen that might be on the order of about 60 feet long from the water table down. It's going to be a much larger diameter well, and it's going to have different slot sizes in it to allow us to potentially pump up to 150 gallons per minute out of the aquifer. And the reason it's put in this location instead of up in the centroid is because we're exploring the possibility of whether or not one or more wells in a location like this right here might have the potential for actually capturing chromium that might be moving in the down gradient direction. So it could be an excellent measure to take to kind of control the plume. To address your question, Stephen, about what is the plume migrating? Well, let's not wait around and find out. Let's maybe try to grab it while we try to tackle some of the complex approaches that might be necessary to manage the centroid itself. So I know people were interested in perchlorate. You don't hear a lot about it, even though it shows up on some of the maps. 2 super quick slides, and then we can field questions later. I can stay around as long as you guys need. But here's the perchlorate plume. And I just didn't show it on the other maps, just kind of for simplicity. But here it is, and we believe it actually has a different source than the chromium. So the chromium surface water pathway came down here, infiltrated in this area, moved this direction, and then became this plume here. The perchlorate plume, we believe, actually started by coming down Mortendad Canyon right here and dropped into the regional aquifer vertically, basically right in this area to create this plume. This line nominally represents the 4 part per billion concentration, which is the screening level that's in the consent order. That's the number we work to. The perchlorate was associated with plutonium processing. That's why it came out of the rad liquid waste effluent. Super important to know that in 2000, or up until 2000, the perchlorate concentrations coming out of the rad liquid waste treatment plant effluent were on the order of, I think, 100 to 200 parts per billion. The laboratory took it onto itself to actually improve the treatment system and brought it down to 4 part per billion in effluent starting in 2000. That same plant has actually gone essentially to a zero liquid discharge mode and hasn't really even released effluent for over 2 years now. We believe that it's creating results like this. So I'm going to go back here. There's a well called MCOI6. It's one of those perched intermediate wells. It's about 600 feet, maybe 500 to 600 feet below the canyon floor. And there's a very interesting trend that actually starts in about 2005 of decreasing concentrations. That's probably because of the improved treatment. But what's profound to us is how quickly that change may have manifested itself this far vertically below the ground surface. So it might be teaching us a lot about how quickly source control can start cleaning up the system by just taking out source out of the environment and letting the system sort of heal itself. And so we're very actively trying to understand the processes here that have resulted in this reduction to see whether or not that the source control measures that have essentially already taken place for perchlorate are going to be the solution for the perchlorate plume itself. That this thing is going to start shrinking on us because the source that was feeding the environment has essentially been reduced so substantially.
Question.
And that is it.
Is the perchlorate plume at the same depth and also
Yes.
like a thin pancake 100
Yes.
feet above?
Yes, it's
Okay.
exactly the same.
So Danny, what would your cleanup level be in the regional aquifer? What cleanup level are you trying to achieve even with natural attenuation?
So we haven't established that cleanup level. Right now, the default is what the consent order requires, which is the standard at 50 parts per billion. But I think with the case with all of these types of projects, you hit a point of feasibility or kind of benefit in return. So we are not at the place yet of being able to work with NMED or being prepared to work with NMED on what ultimately would be, sometimes in CERCLA you hear the term preliminary remediation goal, but I could sort of imagine a situation where, I'll just make up some numbers, where cleanup to 200 parts per billion is considered the amount that you can get sort of with high return, and that might be the cleanup level because the remaining amount can be demonstrated to attenuate through natural processes in the environment over some time period that's considered regulatorily acceptable.
So the 50 comes from the Safe Drinking Water Act, and that's for total chromium. I'm sorry, yeah. It's for total, which is both hexavalent and trivalent. So you would shoot for a situation that's going to lead to less than 50 hexavalent in the...
No. It's called a total chromium,
Right.
but it refers to hexavalent chromium because there is no trivalent chromium in
No,
groundwater.
and that's what I'm saying. So
Right.
in order to achieve that Safe Drinking Water Act limit, you would actually have to remediate hexavalent chromium.
Right.
Down
Which is,
below
which is
50.
all you can get out of the ground, which is all there is to get out of the ground anyway. I hear you ask that question a lot, and I'm not sure, I either don't understand or
Well,
you're
I'm just trying to
check.
figure out what your cleanup goal is.
So the cleanup level right now that we're working to is 50 parts per billion, and it's actually the state standard, not the Safe Drinking Water Act standard. EPA's standard for chromium at the MCL is 100, but we work under the consent order, and we're working to 50 right now is the assumed cleanup level.
Okay,
That's as far as
you're
we've gotten with it. And it
but-
is for total chrome.
And at the same time, EPA is looking at developing a hexavalent chromium standard, which is much lower.
That's what we hear.
Okay.
Yep.
So how will that be
Cross
taken
that
into
bridge
account?
when we get there.
Okay.
To my knowledge, I don't know of any remediation project like this that has been undertaken where people ultimately remediate 100% of the plume to the standard. Because you hit a point where technical and practicability just overrides anything you can do. I mean, you'll spend $10 taking 90% of the problem out, and then you'll spend $100 trying to go after 10%. And that's where it becomes super important to understand whether or not nature can do some of the work for you as well, and whether or not that last 10% can be handled by other means. But we're not there yet.
Something in the environment department, we want you to clean up to a level that would attenuate down below 50.
Presumably, at this point, that's our assumption.
Are you looking at any kind of in situ treatment?
Yes. So we're actually, I didn't really go into it much, but we're anticipating, besides the natural attenuation that may be occurring, the possibility of both in situ biological remediation techniques as well as what I'll call sort of enhanced chemical techniques. So most people know that there's ways to induce reduction in the environment. So you can do that by stimulating microbes that will reduce or quite literally consume chromium as a fuel. And we're looking at ways to stimulate them, real simple ways, or sometimes just applying food for the microbes, which are sugars in most cases. And we're hearing technologies where people are applying green tea. We're looking at, right now our minds are completely wide open. Turns out that someone was asking how quickly does the wetland take care of chromium? Well, there's humic acids in the wetland, and kind of an emerging technology that we're particularly interested in are how well do humic acids create reducing conditions, and could those be applied? So those are categories that I would call sort of enhanced chemical treatments, and then in situ biological treatments as well. But importantly, if we can stop that vadose zone, that mass that I said is still dripping down into the regional, this plume might do a lot to take care of itself without spending a lot of energy in the plume. So we're actually even looking at gas phase reductants where we might get at the pore water that's in the unsaturated zone and trying to lock that chromium up there before it ever even gets into the regional aquifer. And that would just be if we could figure out that that's the right application for our site here, that would really be a potentially very powerful remediation strategy. But I think it's super important to know that a plume like this won't be tackled with any one solution. We're going to be hitting this thing in a variety of ways in as many different positions along that pathway as is necessary to tackle this thing.